ongoing. Total grants sanctioned so far 1.15 crores. He's acted as a special invitee NDU PhD oral defense 4 times. SAR has secured a H index of 16, citation 1326, I-10 index is 24, impact factor gain in 270 from SAI Scopus, and average impact factor is 3.13. Such a wonderful personality. Today we have a second session. I invite Dr. M.Sivakumar sir have a session. Please, sir.
Thank you, Dr. Ramachandran. I will
yes, sir. Thank you, sir.
share my screen first.
Yes, sir. Yes, sir.
Am I audible?
Yes, sir, audible, sir. The screen is visible.
And I'm very much happy to extend my sincere thanks to the organizers, especially the head of the department, Dr. Saravanan, and Ramachandran and his team, YB Kannan, Marikannu, and I know those people very much, and Dr. Ravi Kumar, everybody in the team in physics department, as well as the management of APSA College, the esteemed secretary of APSA College. I must thank for giving me this opportunity to talk on the recent trends in energy storage materials and their alternatives. Actually, I'm extremely happy to mention that, as rightly pointed out by our earlier speaker, that is our registrar in charge of Alagappa University, Dr. Shekhar. He mentioned that the energy materials is the very potential and booming field right now. So the organizers chose the right topic for the discussion among the people right now. In this locality, the geographical location is very remote one. However, the organization of such wonderful conference is doing right now. It's very much appreciable, and I am very much thankful for organizing this conference in my area of specialization. And now, as of now, all of you know about the institutional information of Alagappa University. Right now, we have 41 departments, and we have been awarded with a secured 3.64 out of 4 in NAC during 2007. At that time, it was graded as A+ grade. Right now, in the new scheme, it is A++ grade. So with this short note, I just move on to the presentation, the topic. Why we are need energy. To do any work, we need energy in kind of, it exists in the form of potential energy, kinetic energy, thermal energy, as well as electrical, chemical, nuclear, or other various forms. Almost all the forms of energy are associated with the motion. Actually, while we are coming to the resources, what are all the natural resources of energy? It is almost most of the energy are derived from the bare environment, actually. But nowadays, what we are doing, we are consuming the energy day by day, minute by minute, and it is the demand is almost maximum to the end, so that we are exhausting the globe's reservation of nature resources. Almost in future, it will be depleted due to the industrialization, population of growth, and we are looking for the best economy and the technology today for to develop the countries. Towards this, we need the natural resources, which are not replaceable. So in this aspect, we are dealing with the enhanced materials. How we can do it? Actually, we are depleting the energy sources. Almost 90% of our energy sources. Almost it is coming from the fossil fuel. I hope everyone knows about the fossil fuel. Fossil fuel is மக்கி போறது அப்படின்னு நம்ம தமிழ்ல சொல்லுவோம். அதெல்லாம் வந்து it accumulate in one places and uh, it is identified as the fossil fuel. Later it can be used for the to derive the energy from it. Now, of course, world energy conservation standard prediction, it gives the conclusion that the coal deposit all over the world will deplete within next 200 to 300 years. And of course, when we can consider the petroleum deposits, it will deplete within very few decades. Probably we have come across 100%. Whether Sachin is the only person to score century, and the petrol and the other prices are hiked towards century, they got centuries. So that all the countries are encouraging the R&D activities nowadays with a broad spectrum of possible renewable sources, as their contributions are substantial in the development of any country. Now, we are talking about the energy. What are all the forms of it? Is mechanical energy, electrical energy, chemical energy, as well as the electrochemical energy. So we are mostly concentrating on the electrochemical energy, which are dealing with the batteries and supercapacitors and some kind of conversion device such as fuel cells. In batteries, we are having mostly depend on the lithium batteries, because it gives a lot of advantages are available while we are using the lithium batteries. Portable electronic devices, large electronic devices, dynamical stability, power to weight ratio, everything is excellent as far as the lithium is concerned. And but we don't have much resources. Therefore, we are having the alternates like lithium sulfur, sodium, air battery, and other things. Also, the energy storage devices is mentioned by the earlier speaker as supercapacitors. And a few researchers are very much delighted to have the biofuel, which is focused, very much focused by our former president, Dr. APJ Abdul Kalam. Jatropa biodiesel he encouraged. And now, as far as the all the batteries and the storage devices are coming under the category of solid-state ionics, which is based on the flow of ions in solids at low temperature below their melting points. We are always talking about a battery and other once if we talk about the energy storage, obviously everyone thinks about the battery. So what is battery? It is nothing but the electrochemical cell to store the electricity in the form of chemical energy. There are two types of batteries. One is primary, which is not able to recharge, and the secondary battery, which can be rechargeable. So this is the major classification. And we can see this slide pictures you the overall reaction of battery functioning. And right now we will deal what are all the basics of a battery, how what are all the components, and how it can be prepared, and what are all the factors affecting the commercial batteries. Everything we will see, and we will see some of the works. Maybe I will not discuss much about the in-depth research, and some results I will provide. See, this is the slide. During charging and discharging, once if you take a battery, they are always concerning about the charge and the discharge. Right now we can see this. This is the cathode and this is the anode. This is the intercalated material and this is made up of graphite. These two are cathode and anode are coated on the current collector. Here there is a electrolyte film which separates the anode and the cathode. Now while we are charging the battery, the the lithium is moving from cathode to anode by the ejection of electron from the current. While doing the discharge, the transformed lithium ion is returned to the original position from anode to cathode by the ejection of electron in the current collector of anode. All those things are crossing the electrolyte separator. Here we are using the solid state liquid electrolyte or gel polymer electrolytes. With this, we have our researchers have developed so many modern battery technology. Zinc carbon battery, which is nothing but the dry cell battery. It is very inexpensive. The AA battery like this, and AAA battery like this. Another battery type is alkaline battery, which is commonly termed as Duracell Energizer battery. And the lithium iodide, which is used in the pacemakers and the hearing aids for its longer cycle life. And lead acid battery and nickel cadmium battery are used in the automobile engineering. Also, it was replaced by nickel metal hydride batteries. Out of all, lithium-ion batteries are capturing the advantage like very good power to weight ratio. Often, therefore, it has been used in the all high-end mobile phones, laptop, computers, camcorders, camera, everything. Another type is zinc air battery because it is very lightweight, and zinc mercury oxide battery. Often it is used in the hearing aids. Silver zinc battery also used in the aeronautical applications due to the weight is very less. So out of all the battery technology mentioned here, not only this, my air battery, zinc air battery, magnesium battery, everything is there. I exampled just few. Out of all the batteries, lithium is the noblest material. Therefore, the lithium battery captures the entire market of electronic market, entire place in the electronic market. That is about 63%. You can see the 63% of market has been captured by the lithium-ion batteries. And it has been majorly used in the electric vehicles, EV applications, as well as the power sources for portable electronic devices. And everyone looking for what are all the factors affecting the commercial batteries, which are nothing but the high working voltage. First one is high working voltage. See, this is the Nippo battery. It is rely upon with the 1.5 volt. Normally, everyone knows it is it gives 1.5 volt. Whereas for any cell phone, mobile, you can how many of you open and see the capacity and the working voltage of that your mobile phone? It is made up of LFP, that is lithium iron phosphate based material, and they have given 3.4 volt, and some batteries are giving 4.3 4.2 volt. Like this, we can based on the material, it gives the different working voltage. And we must have a less change in working voltage during the cycling, or it during the discharge. And it must have the high capacity. Everyone knows about the capacity, how much capacity it gives. Based on that, it can be applicable in the different applications. And also, it must have the high Coulombic efficiency and high power. And also it should have a high cycle life. Normally, how many of you know about the cycle life of a battery? Normally, உங்களோட செல்போன்லாம் இப்போ நீங்க இது போடுறீங்களே, சார்ஜ் போடுறீங்களே, எத்தனை தடவை போட்டிருக்கீங்க? ஒரு நாளைக்கு ஒரு தடவை போடுங்க, இல்லை 2 நாளைக்கு ஒரு தடவை போனீங்க. How many times it has been cycled? Probably for any battery, it is normally 2000 times to 5000 times. It is the basic requirement for the battery. As far as the commercial one, it is the requirement. So we need the longer cycle life as well as the chemical electrochemical stability. And most of the batteries are finding this kind of difficulty. Sometimes if you keep this battery for a long time, maybe 1 month, 2 months without any functioning, that is at that time it starts the electrolyte oozing out from the battery. That is called decomposition. So we should not have any decomposition of the electrolyte at any time during the cycling or during the shelf life. So out of all, materials availability is playing a prime role of the commercial batteries, because based on the material availability we can make use of the material, right? Okay, now we will deal about the materials available, materials to be employed in the battery. That is nothing but electrodes such as anode and the cathode, also the electrolytes. Some examples are given here for cathode and anode. This one TAS2 is the very noblest first material while we are employing the lithium battery, TAS2. And we are using the electrolyte film or the separator are used. And many times all the commercial batteries nowadays they are using liquid electrolyte. Due to the leakage issues, we are moving on to all the researchers are moving on to the solid polymer electrolyte or gel polymer electrolytes. Why we are using the polymer? It is having the very dynamical strength, and normally all the polymers are made up of joining the many monomers together and form a chain like arrangement. It gives the polymer. Okay, repeatedly we are arranging for discussing about the ideal polymer. We can have the temperature study, the temperature analysis, the thermal analysis, like dynamic mechanical analysis. And here is the idealized temperature curve of a polymer. It is all the scan of the temperature polymer while increasing the temperature is being like this. And while increasing the temperature, there is a local motions are taken place among the atoms. That temperature called T gamma, and further increase of temperature causes the toughness of the polymer, that gives T beta. And if you keep on increasing the temperature, what will happen? That will become it was transformed into glassy to rubbery state. That temperature is called glass transition temperature, which is very important factor as far as any polymer is concerned. So based on this value, all the polymers are employed in the applications. So see, for highly crystalline material, we cannot get any, we should, they do not have any glass transition temperature, and it keep on like this. Beyond that glass transition temperature, it becomes rubber in nature. And for if there is any crystal slip occurred in the polymer, this plateau is like this. This plateau is like this. And for some amorphous polymer, it becomes the pattern will be like this. Okay, still if you heat it again and again, what will happen? It starts melting. Melting means it transformed from rubbery state to liquid state. So this is the entire picture of polymer for idealized temperature scan. And for sometimes from the rubbery plateau, we cannot, for thermosets, it doesn't have any melting point. So can you say any example for thermoset? I think everyone was muted by the administrator. Maybe I will tell the நம்ம நார்மலா ஃப்ளாஸ்க்லாம் வச்சிருக்கோம் இல்லையா, that is nothing but the thermoset. And based on using the polymers, we are preparing the polymer electrolyte using the conventional solution casting technique. Normally, all the polymers and the salt are dissolved in same solvent. Alkali metal salt was used to do the mobility of charge carriers, and it has been mixed together and stirred for several hours. After that, after attaining the homogeneity, it has been casted and on a Teflon sheet or in a flat bottom Petri plates. Finally, all the solvent was evaporated. Then it is dried under vacuum for several hours, and we can have achieved the freestanding film. You can see the freestanding films little later. Using that electrolyte, all the cathode material or anode material, whatever it is, here I am giving an example. We can have the active electrode cathode material, namely as LiFePO4, and it has been added with the conductive carbon, binder, PVDF, polyvinylidene fluoride, and all the active material, super P or conductive carbon, PVDF are dissolved in the solvent N-methyl pyrrolidone and mixed together using the homogenizer. I will show the video of it, and it has been coated on a aluminum foil. After that, it is roll pressed and slitted into circular shapes. Here we can use the lithium foil, pure lithium foil, as a anode material. That is, we can call it as this type of couple, cell couple, as a half cell. So we have used that lithium foil and the prepared cathode slitted material and the electrolyte film, and in the 2032 cell case, and assembled the cell. Finally, it was sealing under the vacuum and subjected for various characterizations. See, these are all the material, these are all the instruments where we have used in Taiwan, and this is the coating machine. Here we can pour the slurry. Here we can pour the slurry. See, we are pouring the slurry, and slurry, after it is passing through the dryer, and after drying, the anode becomes like this. If we use the copper foil, we are preparing anode, and while we need to prepare the cathode, we are using the aluminum foil. See, after drying that, it has been roll pressed towards to attain the proper contact between the electrode and the electrolyte. See, this is the actual electrolyte film. These are the lithium foil, and these are all the cell cases. After fabricating this, we have sealed using this vacuum sealer. It has been vacuum sealer. Probably it gives 100 tons at the time pressure. Then all the material batteries have been fabricated in the dry room atmosphere with a -45-degree dew point. Hope you have seen this in some films. See, I will show a few videos. Hope it will be displayed. Sir, idhula video varuma? Adha nalla irukum. கொஞ்சம் பார்க்கலாம். வந்துச்சு அப்படின்னாக்க ரொம்ப நல்லா இருக்கும். Because it is a rare opportunity where we have worked in ITRI, Industrial Technology Research Institute, which is situated in Taipei, Hsinchu, Taipei. The maintenance of this room itself cost about more than $500 million per month. So it is very expensive dry room facility in Asia. I think it is number 1 in all over world. See, and we have stirring for several. Hope it is visible, right, sir? See, this is the slab where we can pour the slurry. This is the area. Here, hot air is passed, and the material has been dried here. Okay. Now we can see this one. So this is very interesting. If it is visible, maybe bear with me. தெரியுதா ராமச்சந்திரன்? ராமச்சந்திரன் தெரியுதா?
விசிபிளா இல்லைங்க, தெரியலைங்க சார். அது ஆமாங்க சார். உங்க ஸ்கிரீன்ல அதோட ஆப்ஷன் கீழ இருக்குமா சார்? அதை மேக்ஸிமைஸ் பண்ணீங்கன்னா எங்களுக்கு தெரியும் சார்.
அப்படியா?
ஆமாங்க சார், அதான் டெக்னீஷியன் அதான் சொன்னாரு. இப்ப
எப்படிங்க?
உங்க ஸ்கிரீன்ல கீழ வந்து அந்த ஆப்ஷன் இருக்கும், அதை மேக்ஸிமைஸ் மட்டும் பண்ணோம்னா தெரியும் அப்படின்னு.
அப்படியா?
கொஞ்சம் ட்ரை பண்ணுங்க. ஆமாங்க சார்.
பாக்குறேன். இல்ல அப்படின்னா we can skip this.
ஓகே சார். ஓகே.
ஓகே, வரல ராமச்சந்திரன்.
ஓகே ஓகேங்க சார். ஓகே கோ அஹெட் சார்.
ஓகே.
sorry, coin cell assemble slide number. Okay sir, it's not a video.
Okay sir, if possible after finishing this we can see the video, sir. These are all the coin cells we have prepared. The coin cell arrangement are given here, and the dimensions of the coin cells are given in the right hand side. This spring has been used to give the proper pressure for the cathode and the anode. Electrolyte cell. தெரியுதா?
தெரியுது சார். ஓகே.
And okay, the here you are seeing the polymer electrolyte film. These are all the lithium foil, and these are all the cases. Based on this, we have prepared the coin cells and subjected for various characterizations like AC impedance, LSV, lithium ion transference, charge discharge, cyclic voltammetry, everything. And we have prepared the polymer electrolytes, PVDF polymer electrolytes with EC and PC, along with the different alkali metal salts like triflate and BF4 and ClO4. We can visibly seeing the changes in its surface morphology. And all the electrolyte materials, sometimes electrode materials have been prepared and subjected for analyzing the functional group vibrations and using the FTIR. And this assignment gives you a clear picture about the assignments of functional vibration groups. For example, OH stretching vibration have been occurred during 3600 to 3000 centimeter inverse, and C double bond O is around 1630. Like this, we are assigning the functional vibrational group of the material. And based on this shifting and absence or appearing new peaks, we can conclude the happening of complexation in the polymer matrix. And see, this is the dynamic mechanical analysis of PE polyethylene methacrylate and polymethyl methacrylate, how much in the same family itself, how much difference it has. You can see the Young's modulus. Using this, we have seen we are seeing the cyclic voltammetry of the prepared electrolyte film, that is gel polymer electrolyte film, using the PVDF and the PEMA, LiClO4 and ECPC, with the FePO4 and Li, lithium cell, that is nothing but a half cell. If you use this here also, the intercalated material anode, it is called as a lithium ion cell, that is a full cell. It is performed under the scan rate 5 millivolt per minute, and see the oxidation and perfect oxidation and reduction of LiFePO4 happening at 3.7 and 3.2 volt. Of course, we have seen something about the electrolyte, and we are going to see about the preparation of the cathode material and sometimes anode material. And those are all based on the structural aspect. So there are three types of structure. One is one-dimensional, two-dimensional, and three-dimensional. Most of the olivine type materials are coming under the category of one-dimensional, and for two-dimensional layer type and the three-dimensional spinel type materials are occurring. So these are all the most prominent commercial cathode material. LiFePO4, normally we are calling it as LFP, and this one is the LCO, LiCO2, and the spinel, it has multiple electronic states. Almost all the materials are followed the BRAVAIS lattices. We have any one of the 7 lattice types and 7 unit cell types, and there it has 14 BRAVAIS lattices, like cubic, tetragonal, orthorhombic, hexagonal, monoclinic, triclinic, and trigonal unit cell types. See, all the alpha cell parameters are differing given here. For cubic, A equal to B equal to C, and gamma, beta, alpha, beta, gamma is 90 degree, and for each and every case it differs. So based on that, it gives the unit cell type. Okay, let us take the commercially successful cathode material in one-dimensional, two-dimensional, as well as three-dimensional. This one is, oh, now only it is coming. So I think இது வருது, அந்த வீடியோ வருது, கொஞ்சம் பாத்துருங்க. இது தெரியுதா சார்? வீடியோ தெரியுதா?
இல்ல சார், இன்னும் வரல.
வரலையா?
வரலைங்க சார்.
வரலையா?
கம்பேரிசன் ஆஃப் கேத்தோட் மெட்டீரியல்ஸ் அந்த ஸ்லைட் தான் சார் இருக்கு.
சரி, அப்ப நான் இத க்ளோஸ் பண்ணிடுறேன். ஓகே, அப்ப நான் க்ளோஸ் பண்ணிடுறேன். Okay, sir. It is completely based on the structure. It has a layered structure. LiMn2O4 is coming under the spinel structure, and LFP is coming under olivine structure. It has the theoretical capacity normally of 273, 148, and 170 milliampere hour per gram. How we can attain from the each and every material? For two-dimensional, we can attain only 160 out of 273, and 120 out of 148. Whereas we can attain the almost the theoretical capacity of LiFePO4 practically. So at a 3.4 volt operating voltage. However, we are finding some hitches in terms of LiFePO4, which is nothing but the poor electrical conductivity and diffusivity. However, it is very stable and low toxic. Price is also a little bit cheap. Whereas these drawbacks like poor electrical conductivity, poor diffusivity are to be enhanced or encountered. Of course, all the materials like LiFePO4 or other cathode materials and anode materials are prepared using the common co-precipitation method, which is used by your convener Ramachandran. He prepared several CO2 electrodes using this prominent method, co-precipitation method. And we have a Sol-Gel method, in which raw materials are dissolved in DI water, and after continuous stirring, the chelating agent has been added to jellyfy. Then further it was decomposed more than 500 at 500 degrees centigrade, and sintered at 700 to 800, or sometimes more than that, sintered, and finally we can attain the product. Like this solid state reaction, which doesn't require much practice. Just we can here mix all the raw materials and decompose it. Then it is heated around by 800 degrees centigrade and cooled it to the room temperature. Then we can get the final powder. Like this solution method are available. And there is one method which is used at low temperature to prepare the electrode materials, which is nothing but the polyol process. It is the energy efficient method. What does it mean? We can prepare the electrode acetate precursors and acetate precursors and iron precursors combined together and dissolved in the polyol solvent, which after that it has been refluxed to the boiling point of polyol solvent and refluxed for several hours. Finally, it has been washed and dried for half a day or 1 day. Then we can attain the very nanocrystalline size material using this energy efficient method. We are not adopting any high temperature. We are not adopting any high temperature method in polyol process. So based on that, DK Kim and JK Kim have prepared LiFePO4 with the space group of PNMA, and you can see it gives the very much rod-like structure. See, that's why I asked Dr. Shekhar how you have attained. Like this, it is also the patented material. They have practiced several pros and cons, and they have attained this material with a rod shape, a very minimum shape. It is about, you can see the nanocrystalline size of this prepared LiFePO4. This is the TEM images. You can see the orientation, and the 10 nanometer by 50 nanometer breadth and the length, you can see, and some rod shaped particles. They have patented the polyol process of LiFePO4. We have used that material for preparing the olivine type materials in sodium battery also. This is the SEM images of some branerite AB206 type electrode material. It is used as the anode material. You can see the growth of this branerite electrode. And the TEM, also the SAED pattern of that branerite electrode. See, in this at the point 1 C, it attains 170. It attains 170 milliampere hour per gram. What is the theoretical capacity of the material, the LiFePO4? It is 170. So we have they have attained 170. We have also attained the 170 milliampere hour per gram by means of using some carbonaceous material with sulfur. These are all the electric vehicles prepared by our energy materials lab group in ITRI, Taiwan. Okay, let us come to the core topic. It is the alternate. I want to talk about some alternative materials like Why we are going for lithium? Lithium is a noblest material which has the high power and energy density. So with this my energy density, why don't we continue all along? But what about the resources? Whether we have the resources in India? No, definitely not. So we have some resources in some Europe countries, US, as well as in Australia. Other than this area, where we have very rare resources, lithium resources. So that obviously we need to go on to the next alternative. Even though it exhibits a very good property, very good electrochemical properties, and excellent dynamical stability, everything. Whereas we need to go for the alternative because of the major criteria is material availability that was seen in the important factors affecting the commercial batteries. So towards this purpose, we are looking for the alternative. The sodium material is the noblest one, the next noblest one. Why? Because it is abundantly available. That is everywhere we can see, and we have the lot of resources in India also, and it is a little safer than the lithium, and it has the similar electronic property, electrochemical property as such the lithium. So therefore we are moving on to the materials like sodium or sulfur. Sulfur is also a material, 10th prominent material which is used for fabricating the lithium sulfur batteries. Nowadays we are also doing the sodium sulfur batteries. Now these are all the advantages of sodium battery. However, we can have the major drawback is the ionic radius, cationic radius of the sodium. That is 1.02 Armstrong unit, whereas the lithium is having 0.7 Armstrong unit. Right. So these are all the criteria, which is cost-wise it is low, and lithium gives a very high cost, and the technology should be. And moreover, one important point we would like to say: lithium needs a special atmosphere to proceed further to fabricate the electrode, batteries, and other things. Why? Because if we expose the lithium in air, what will happen? Lithium becomes lithium hydroxide immediately. கருப்பா போயிடும். இப்போ நீ வெளியில நல்லா ஒரு மாதிரி சில்வர் கலர்ல இருந்தது இல்லையா? If you take it out from the glove box, it obviously becoming LiOH, and it forms a dendrite, and we need to have the inert atmosphere almost. Otherwise it becomes a dendritic formation, and the immediately that affects the electrochemical quality properties of the material batteries. So towards this we have moved on to the sodium material. It has prepared with two structure. One is layer structure and another one is olivine type structure. And layer structure is classified into four major types. One is P2 and O2, P3, O3. Here the P stands for the prismatic site. The sodium is situated at the prismatic site, and in octahedral site, O refers to the octahedral site, and the 3 refers to the actual content of it. It is nothing but the atomic arrangement. P2 type has the atomic arrangement of AB, BA, AB, BA, whereas the O3 type AB, C, AB, C, AB, C, like this. The P2 and P3 and O2 types are a little bit tricky when compared to the P2 and O3, because for that reason P2 and O3 are prominent layered material for sodium batteries. See, while we are considering the one dimensional, that is olivine type, there are two types of classification. One is maricite and another one is olivine type. That is Here the maricide has the edge sharing, edge and the corner sharing will be explained in the next slide. See, maricide has the edge sharing, and therefore it doesn't have the flow of sodium ion. It restricts that. There is no channel, further channel, whereas the corner sharing gives the channel for sodium atoms to move further. See, this is the shapes octahedral, prismatic, and tetrahedral. In octahedral, the faces you can see very clearly. The faces are 8. The faces are 8 in the null. Adhe mari that side we have another 4 faces. Corners, corner 6. See. See, this one is the corner. 1, 2, 3, 4, 5. Here in that side, if you consider the 3 dimension, this one. So 6 corners and the edges, 12 edges. See, 1, 2, 3, 4, 5, 6, 7, like this, and the back. We have 12 edges. Like this, faces and the corners of the prismatic and the tetrahedral structure are given here. The major limitation of the olivine type maricide structure is we cannot it is electrochemically inactive due to the cationic channel is very much deficient. So the olivine structure has the ion exchange channel, so that it is most of the time olivine type structure has been formed to use the fabrication of electrode material to employ in lithium sodium batteries. For some example, we have prepared the synthesis and maricide NaMnPO4 by making the maricide in to electrochemically active and participate in the electrochemical reaction by means of a polyol process and with various precursors. We have used several precursors such as manganese acetate, manganese chloride, manganese chloride, manganese sulfate, and manganese acetate precursors. But out of which we have prepared the acetate precursor using the acetate precursors, it forms very well NaMnPO4 with this structure. So it exhibits see the charge discharge of this battery while using the chloride and sulfate precursor. It exhibits just 1.64 milliampere and 5.07 milliampere hour per gram for chloride and sulfate. Whereas while using the acetate precursor, it gives 102.67 milliampere hour per gram, and it sustains up to 100 cycles with 54 milliampere per ampere hour per gram. That gives the conclusion that the manganese chloride and the manganese sulfate precursors employed materials exhibit a very poor electrochemical performance due to the high acidic nature of the polyol solutions. That will wash the solution and it causes the poor crystalline formation. Therefore, while using the manganese acetate precursor, we are expected that the well crystallized pure maricide NaMnPO4, which gives the good electrochemical properties such as 102 milliampere hour per gram, and it also sustains very well. We have also prepared some high capacity prismatic type layered electrode with anionic property for the efficient as an efficient material. We have prepared using the sol-gel and solvent very prominent solution solid state reaction. We have see this this figure. We have prepared the very lengthy electrode, and we have made the pouch cell also. Pouch cell making is not an easy one, but in our lab with very minimal facility, my student Mr. Arjun has prepared, and he has tested also. see the SEM, TEM images and SAID pattern of the particular material prepared using the sol gel. It it gives the hexagonal type P2 type structure, and it exhibits the greater than the original theoretical capacity. Original theoretical capacity of such material is sodium nickel manganese oxide is 173 milliampere hour per gram. Whereas we got more than that, that is around 244. It is due to the in the voltage range 1.8 to 4.5, while we are using the NaPF6 in propylene carbonate. This is because of the anionic redox reaction of the material of the P2 type NiMnO2 material. However, it is very high and abundant one, therefore it also it exhibits a very good electrochemical properties. Whereas while we are using this material, this pristine P2 type material, we are suffering from the high voltage charging. During that high voltage charging, there is a interlayer expansion due to high voltage charging, and there is a sliding is occurred among the transition metal layer. Then suddenly it creates the vacancy, Ni vacancy. That Ni vacancy has been equalized or neutralized by means of adding the inactive, electrochemically inactive Zn into it. It holds the structure. So that has been proven by our experiment, and to maintain the very good cycle life and with the good electrochemical properties and performance. See, these are all the results, and here also you can see the stack-like arrangement, sequential layer slips are occurred during the charging and discharging, therefore during the preparation. So it has been replaced by the Zn atoms, and see the little bit polycrystalline type arrangement has been occurred. And while we are incorporating the Zn in different ratios like 0.01 and 0.07 and 0.1, while we are using the 0.1 of Zn, it gives a very good electrochemical property, and it gives around 205 milliampere hour per gram. Whereas while 0.07, it just drags around below 200. So it can be used in the potential window 1.5 to 4.5. It has been compared with several researchers earlier reports, and we have stands first. That Zn substitution strongly overcomes the technical hitches of this P2 type NaNiMn ZnO material, entangling its structure by means of the valence close to nickel, and it holds the P2 type structure upon cycling. But it doesn't affect the P2 type structure layer structure. And to the best of our knowledge, we report the maximum discharge capacity of 205 milliampere hour per gram in this voltage range 1.5 to 4.5. Okay, we can have a very quick look of P2 type sodium electrode. We have prepared the PVDF SiO2 electrolyte membrane and employed in this sodium electrode. We have attained 174 and tested in this range 2.0 to 4.0. And we have prepared some carbon material using the biomass coated TiO2, and also we have prepared e-waste. E-waste is nothing but in the printer cartridges, used cartridges, we have some powders that has been used as the carbon source. And we have coated that carbon on the Fe3O4, and we made the anode material for this sodium electrode, and it exhibits a 410 milliampere hour per gram and tested as a full cell. Also, this Zn based material has been used as the cathode. finally we have attained the full cell configuration using this ZN substituted P2 type material, and also e-waste based carbon coated Fe3O4 material, along with the PVDF SiO2 electrolyte film. See, this is done by my student Mr. Arjunan, and he prepared the pouch cell in terms of all shapes. He prepared the pouch cell. See this pouch cell, and we have made the contacts. And I'm very proudly announced that we have developed a battery, plastic battery. It is nothing but the Amurdanjan டப்பா இருக்கு இல்லையா, அதோட கேப், the lid of Amurdanjan bottle, it has been used as the material to prepare the sodium battery type, and it has been tested. We have developed fabricated a battery using our material in the battery cap, Amurdanjan cap, and we have run the household article like the digital clock as well as the analog clock, and we have used through the transistor. It has for the amplification purpose. So we have succeeded with this material by our student Mr. Arjunan. I am very much happy to announce this. And another material we have prepared, cobalt doped layered lithium nickel oxide, which has been prepared as a 3-in-1 electrode for lithium ion, sodium ion, as well as the supercapacitor applications. So normally it is very difficult to find one material can be employed in 3 applications. So we have made it possible by my team member, Mr. Divakar, Dr. Divakar. He has prepared this material, and see the cubical size. It has been prepared while using the cycle voltammogram, various rate capability, the cycle life, and other things, the specific capacity of this material. So it has been versus lithium metal. It has been shown. See the possibility of lithium metal, how it goes in, how it performs with the good electrochemical properties. It gives around 250 milliampere hour per gram. Whereas while using it in the sodium battery, it also exhibit around 210 milliampere hour per gram with the similar type of rate capability, and CV gives you the possibility of intercalation of sodium material into the LNCO. Also, it has been used in the supercapacitor application at 0.5 ampere per gram. It exhibits around, it possesses around 320 farad. So based on this, everyone has the question in their mind such that sodium ion intercalated into the LNCO material, the presence of anodic and the cathodic peak in the CV of sodium battery, which gives you the possible intercalation diffusion of sodium ion into the LNCO. So this gives you, this is correlated with the XRD as of the LNCO is 4.73 Armstrong unit with the layer distance, and it has. But we know that it is having the sodium ion has the ionic radius of 1.02, so which can be very much easily penetrated into the layer type. So this is the possibility of usage as usage in sodium batteries. We can make use of the 3-in-1 electrode also. So I think we will stop with this because the time is running off. Maybe fuel cell is also a conversion device which can combine the hydrogen and oxygen to produce the electricity with the water and heat as the byproduct. maybe it is the conversion device. In some other session, we will see the actual functioning and other things. So with this, I would like to conclude. I will conclude that all the polymer gel electrolytes can be prepared using various approaches by means of blending copolymers, adding the plasticizer into it, and introducing the ceramic particles using the conventional solid solution casting technique. Also, the prepared electrolytes are very much thermally stable beyond 140 degrees centigrade with the acceptable transference number 0.7 to 0.9 with a good cycle life. So based on the preparation method, various preparation method, the one-dimensional, two-dimensional, three-dimensional materials can be prepared for the fabrication of electrode materials were prepared for the fabrication of lithium batteries, sodium batteries, and sometimes it can be prepared for the 3-in-1 applications. So that alternative sodium batteries display a better electrochemical performance on par with lithium. Therefore, we are moving towards the lithium to sodium and sodium to another air battery, something like that. We are moving. Everyone, life is to like this. We should move on further and further. We cannot sustain in the same state for a long time. So that we are looking for the alternative, and this is the one is a better choice for the alternative energy materials. Hope you have enjoyed the presentation, and if I am boring, maybe I feel sorry. I'm very much thankful to the organizing members of APSA College and the administration of APSA College. Thank you very much for the given opportunity, and you have organized very nicely as commented by me. Thank you very much, Dr. Ramachandran, Dr. Saravanan, and Dr. Marikannu, everyone. Thank you very much. If you have any questions, let me know.
So is there any queries? Okay, sir, there is no query, sir. Thank you very much for your informative talk, sir. It's been very energetic and also very informative. You started from a very basic level and finished up to the recent development of the materials based on energy harvesting devices. Thank you, sir. It's motivated the young researchers to do the new problems in their future. I'm sure that the people are very much motivated your talk. Thank you very much, sir. Thank you.
Thank you, Ramachandran. Thank you, Saravanan, sir.
Thank you.
Marikannu, madam, thank you.
Thank you, sir. Thank you, sir. Thank you.
Bye. Shall I signing off?
Bye. Yes, sir. Yes, sir. Please.
Okay.
Thank you, sir. Thank you, sir. Thank you for.
Thank you very much, sir. I am Ravi Kumar.
Thank you.
And then, sir.
சார் கேக்குதா?
கேக்குது சார்.
ரவிக்குமார் சார்.
கேக்குது சார்.
சார் அடுத்த இன்ட்ரோடக்ஷன் சீஃப் கெஸ்ட் யார் சார்?
அடுத்தது
அண்ணன் சார் நான் கொடுத்துறேன்.
கொடுத்துருங்க சார்.
சரவணன் சார் கொடுத்துட்டாரு சார்.
ரைட் சார் கொடுங்க.
Introduction to chief guest. Good morning to one and all. I have great pleasure to welcome our chief guest, Dr. R. Ilangovan, Professor, National Center for Nanoscience and Nanotechnology, University of Madras, Chennai. I am very happy to invite the postdoctoral fellow of